All right, let's dive in. Today, we're going to go on a pretty cool journey, starting with something super simple, like just pushing a box across the floor, and see how it leads us to one of the most fundamental, unbreakable rules of the entire universe.
So, let me kick things off with a question for you. What could pushing a heavy box and an apple falling from a tree possibly have in common? I mean, they seem totally unrelated, right? Well, the answer is that both of these things, and really everything else, are all about the transfer of one thing: energy.
And to really get a handle on that energy transfer, we've got to start with a word you probably use every single day: work. But in physics, this word has a very, very specific meaning, and it's the key to our whole story.
You know, in normal life, you might say you're working hard, just thinking about a tough problem. But in physics, nope. Work is only done when a force you apply actually makes something move. So if you push against a brick wall with all your strength and it doesn't budge, you've done zero work. It's that simple. Work is the transfer of energy through motion. Okay, so to do work, you need three ingredients. First, you need a force. That's your push or pull. Second, you need a displacement. The object has to actually go somewhere. And third, and this is a really clever part, the angle between your force and the direction of motion is a huge deal.
Physics wraps this all up into one neat little formula: work equals force times displacement times something called the cosine of the angle. Now, don't let that cosine part scare you. It's just a mathematical trick for saying that only the part of the force that's pointing in the same direction as the motion actually does any work. And we measure all this energy transfer in a unit called the joule.
In that angle, it changes everything. If you're pulling forward, you're doing positive work. You're adding energy to the system. But if a force like friction pulls backward while the box moves forward, it's doing negative work. It's actively removing energy. And get this: if you pull straight up on the handle while the box slides sideways, you're doing zero forward work. The direction is key.
Okay, so let's go back to that first case, where we do positive work on the box. We've just pumped energy into it. So where does that energy go? What happens to it? Well, a lot of the time, it does something pretty obvious. It makes the object speed up.
Yep. When the total or net work you do on something is positive, that thing accelerates. It goes from whatever speed it started at to a faster final speed. The energy we just transferred by doing work has transformed into the energy of motion.
And this energy of motion has a special name, of course. We call it kinetic energy. It's the energy an object has just for the simple fact that it's moving. The work we put in was converted directly into this kinetic energy. Now look at the formula here: 1/2 times mass times velocity times squared. That little squared is a game changer. Think about it. If you double an object's mass, you double its energy. But if you double its speed, you quadruple its energy. Speed has this massive, outsized effect on kinetic energy.
And this all leads to a really beautiful, direct connection called the work-kinetic energy theorem. It says the net work you do on something is exactly equal to the change in its kinetic energy. It's a perfect one-to-one trade. You put in 10 joules of work, you get exactly 10 joules of new kinetic energy. That's it.
But wait a second. What if you do work on an object, but its speed doesn't change at all? The change in kinetic energy would be zero. So where did all your work go? Did the energy just disappear?
Let's think about this. Imagine you lift a book off a table. You're applying an upward force, and the book moves upward, so you are absolutely 100% doing work on it. But what if you lift it really slowly and steadily, at a constant speed? Its kinetic energy isn't changing, so where did those joules of work you put in actually go?
Well, the energy wasn't lost. It was stored. It got converted into another kind of energy called potential energy. Specifically, because you were working against the force of gravity, it became gravitational potential energy. It's energy that's now just sitting there, stored in the book, waiting to be released, all because of its new, higher position.
And the formula for this is super intuitive. The potential energy you stored is just the object's mass, times the strength of gravity, times its height. That's it. The higher you lift it, the more energy you're packing away for later.
Okay, so now we have these two big types of energy: kinetic, the energy of motion, and potential, the energy of position. And when you put them together, well, you uncover one of the most profound principles in all of science.
First, let's just give a name to the sum of the two. The total mechanical energy of a system is just its kinetic energy plus all its potential energy. Think of it like the total energy bank account the system has.
And here it is, the big one. If your system is isolated, meaning no outside forces like friction are messing with it, that total mechanical energy is conserved. It never, ever changes. The amount you start with is the amount you end with, always. Energy can slosh back and forth between kinetic and potential, but the total in that bank account stays exactly the same.
This idea is summed up in one of the most famous and powerful statements in all of physics. Energy cannot be created or destroyed. It can only change from one form to another.
And you can see this perfectly with a falling ball. At the very top, before it's dropped, it's all potential energy and zero kinetic. As it falls, the potential energy goes down, but its speed, and therefore its kinetic energy, goes up by the exact same amount. Potential is flawlessly converted into kinetic, and the total energy remains constant the entire way down.
So, now that we've found this incredible conservation law for energy, you have to wonder, are there other things in the universe that are also conserved like this? And the answer is a big yes. Let's take a quick look at another one, momentum.
So, linear momentum is just an object's mass times its velocity. You can think of it as its quantity of motion, or maybe how much oomph it has. And guess what? Just like energy, if the system is isolated, the total amount of momentum before something happens is the exact same as the total amount after. It's another one of these fundamental, unbreakable rules.
Collisions are the perfect example. Before two pool balls hit each other, you can add up their individual momentums to get a total. Then they collide and bounce off in different directions with new speeds. Their individual momentums have totally changed, but if you add up the new momentums, the total for the whole system is identical to what it was before. Momentum wasn't lost, it was just traded between the balls.
And that brings us to a final thought. We started this whole thing just by pushing a box, and we ended up uncovering these incredible cosmic rules about the conservation of energy and momentum. It really makes you wonder, what else out there in our universe is governed by these beautiful fundamental laws?